Everyone, welcome to Simulation. We have a very special guest today. We are going to be talking about the cosmic perspective. We have Jill Tarter.
Hello, Alan.
Thank you for coming on to our show.
It's my pleasure.
Greatly appreciate it. And what a tremendously important subject. And I think it's, like you've called it, the gateway drug for science and for just caring a lot about the small pale blue dot and sustainably progressing moving forward in the future. So how long have you been attracted to astrophysics and space in general, and the search for extraterrestrial intelligence? What was your aha moment? Because for so many kids, we were talking about this when we were sitting down this last week, and there's all these aha moments. Kids get to see Saturn's rings through telescopes, all this different kind of stuff. So what was your aha moment that got you in, and then tell us a bit about the journey that led you to being the director for the research at SETI as well?
Well, I have an undergraduate degree in engineering, so I got a really good education in problem solving. But at the end of that time, I realized that the problems that my engineering colleagues were working on were not the ones that were particularly interesting to me. So I had the luxury of staying around in graduate school and taking a bunch of different courses. And I took a course from Edwin Salpeter at Cornell on star formation. You know, stars have a life cycle. They get born and they live, they die in different ways. And I thought, aha, these are interesting problems. And so I switched my major to astrophysics and got a PhD in astronomy and astrophysics. So that was my eye-opener, my key moment.
And so, okay, so you were like, okay, stars have a life cycle. They're so fascinating to see the stardust, and then the stars live, and then the stars supernova, and not all the time,
no,
and then die, and then the slow kind of build up over time of understanding more and more about space and all of its different vast interests. And so, okay, so what was the thesis in at the time?
I did a thesis that had many parts. It was huge. It talked about galaxies within clusters, spiral galaxies, as they move through clusters which are not devoid of material. There's actually background gas and dust. The gas within the galaxies gets stripped out by something we call ram pressure stripping. And then I also worried about tiny little stars that form and collapse and try to fuse hydrogen to helium at their cores, but they just don't have enough mass to ever get hot enough at the core for that fusion to become sustained. And so they eventually just die out and are dark. And we wondered whether, back in the day when we were beginning to understand that there was mass that we couldn't account for, we used to call it the missing mass problem. We wondered if these little stars could be responsible, and I spent a lot of time trying to figure out what they would look like, but I could never numerically paste an atmosphere onto my model for the central star and get a reliable prediction of a color temperature, which would have told astronomers how to look, at what wavelength to look. So I called them brown dwarfs, because according to Edmund Land, brown is not a color. So I wouldn't be misleading anyone. And it took 25 years to actually find the first one, and now they're a very favorite topic of study, and they're exotic and very numerous, actually.
I can't quite get over how important it is that our show is called Simulation in many reasons, because we strive to expand people's awareness to the potential of the vastness of the cosmic perspective and what could have evolved on other stars and what life would be like there and all that interesting stuff, as well as the idea of once you gain enough power of going into these virtual worlds, how are we not just in one right now? And so when it comes to talking about star systems, I mentioned this statistic to you as well, that 1/3 of all star systems are binary or multiple star systems, which is so unique and interesting to think about that. Now, one out of every star has at least one planet orbiting it.
Statistically speaking, yes.
And that's also mind-blowing. 1 out of every 5 has a planet in the habitable zone orbiting it. where the conditions for life evolving are, just right.
Might be.
Might be just right. And they're just, and the instruments are becoming better and better. You've seen a tremendous amount of change over your career now in terms of the instruments. And this includes both things like Arecibo for SETI, the Allen Telescope Array, but also things like the Kepler telescope for exoplanet hunting. So tell us. I know we have some really good slides to show as well, so we'll get to those. Tell us about kind of the last maybe decade or two of work and what.
So when I was a graduate student, we had 9 planets. Actually, we've lost one of those, but we had 9. We didn't know whether planets were around other stars. We had no clue. And what it took was a lot of hard work and technology development in order to be able to do the observational tests that allow us to infer the presence of a planet, because with very few exceptions, we never see the planet. We only see the actions that it causes on its host star. So it was 1 week shy of 25 years between the time that Bill Barucki and Audrey Summers published the first paper on looking for planets by noticing that if they passed in front of their star, they would block some of the starlight. Almost 25 years from that paper to the day that the Kepler spacecraft launched, which finally gave us the ability to stare at hundreds of thousands of stars simultaneously and notice if they dimmed, if they blinked, and keep track of that, and then look to see if they did it again, and then a third time with a regular period that would allow us to infer planets. We had some techniques from the ground that could see a planet tugging on its star back and forth, but
that's called a Doppler shift.
That's a Doppler shift, right? But only for very massive planets. It was Kepler that gave us entree into the realm of smaller planets, and wow, did that change everything?
Yes.
I mean, we now know there are more planets than stars in this galaxy,
yes.
And we know that they are in systems with architectures very different than the solar system that we inhabit. And so now we have a lot of examples to help us understand this process of star formation and planet formation.
Yes. 25 years is such a short period of time, and to go from not knowing any other star systems in terms of the planets orbiting them to now knowing 4,000 exoplanets.
Yes.
That is crazy interesting.
That's a revolution.
Yeah.
And it's part of the revolution we're currently experiencing. The other piece of that is extremophiles. Yeah. Again, as a student, I was taught that if you had life, in order to have life, you had to have sunlight, you had to have neutral conditions, couldn't be very acidic or basic, had to be between boiling and freezing points of water, couldn't have too much pressure, all of these things that we have now just shown to be completely incorrect. Mm-hmm. It stemmed from our seeing ourselves as the pinnacle of evolution, and of course, if you want life, then it has to have conditions that are conducive for us. But we're not all of life, right? Life is amazing and occupies all kinds of real estate on this planet. And now we know there's a lot of potentially habitable real estate beyond our solar system. So it's a fabulous time to be asking questions about life beyond this planet.
Yep. And this means everything from the ocean floors and what lives there. This is, if on our planet, this is everything from the battery acid?
Yeah, boiling battery acid.
Boiling battery acid?
Yeah, go to Yellowstone and you'll find life in these pools around volcanoes that are just hugely acidic and very, very hot, and such a surprise.
Yeah. And these are extremophiles, and there's exoplanets, extremophiles. These seem to be, two of these most kind of mind-expanding possibilities.
Right.
Yeah.
Who knew?
Who knews? Okay. And then that's a massive shift. And then this is thanks to, like you said, these instruments that we developed to be able to do this. So Kepler went up and looked at one patch at the first mission. That was Kepler, and then K2 went and did a different mission once a reaction wheel blew
Right.
out. But this like you said, the importance of looking at one patch of sky was that so you could verify the dimmings when the planet would transit in front of the star. Then you could see the dimming, and then you would wait maybe a year or 2 years or however long the orbital period is, 10 days, and then you would verify that it did a second time, it did a third time with the dimming. And so this is how to conduct science.
Yes, indeed. And Bill Barucki, who was the principal investigator on that mission, was incredibly tenacious. He had to propose that mission multiple times, get turned down, go back and make it better, till it was finally accepted, and they actually made it work on the sky.
Yeah. Oh, I'm so grateful that we collected all that data. And now, okay, so are there other really important pieces to kind of giving us this cosmic perspective about the last 20 years?
Yeah, my colleagues and astronomers in general have a really privileged point of view, right? We have a different way of looking at here and now, probably quite different than you might have been thinking when you got up this morning. Mm-hmm. But we really need to rethink what we mean by here and now in this larger cosmic perspective. So here, right? Mm-hmm. Here we are. That's where we are.
Yes.
And that's in a building on Market Street.
Yes.
And that's in San Francisco. And Google Earth now lets us be familiar with that. And in fact, from the altitude of the low Earth orbit satellites, we're on the western part of the United States. And we know that we're here on Earth. And this is a selfie of Earth. Whoops, we've got it. So
yes.
This is since 1968, when Bill Anders took this photo coming around the limb of the moon. We've begun to see ourselves as one body in the vastness of space.
Yeah.
And that's a really amazing perspective, because there are all kinds of challenges that we have on this planet that don't respect national boundaries, that are going to require us to have this global enterprise in order to solve them. And it's going to be really hard to get there if we can't put ourselves in the right framework and understand this system, this wonderful system that we live on this planet.
It's a playground for many, whatever they are, And
you're right. On the human level, if we can't figure out how to be in full collective harmonious control as well as balance with the ecosystems that exist here, we're going to experience some problems moving forward. We already have experienced lots of problems leading up to this point, and I'm very grateful that we've even made it to here. But we got a lot of work going moving forward. So this is Earthrise.
Right.
And this gives us the first sort of perspective of the overview effect. And actually, I think that if more politicians and just people in general were able to be here physically, I think it would accelerate us towards that sort of
Right. Actually,
progress.
there are a number of groups that are trying to enable that, targeting young leaders, the future leaders around the globe, trying to give them opportunities to get up into the stratosphere, to actually see the Earth, to see that fragile, fragile layer of atmosphere that protects us.
Yes.
And have them take that experience forward as they begin to take their place and shape the world of the future.
Yeah. I really look forward to all of those projects and driving the cost down as well to make it as affordable as possible for people to go up and have their perspective shifted that way. So Ron, go ahead and go to the next one.
So again, this is a selfie of Earth. This is right below that tip. There's a little dot. That's us. That's everything. All of us.
This is taken by Cassini.
It was taken by Cassini, right? And we sent out a memo and suggested you go out on the lawn and wave hello, right, as this was taken. But the next slide will show you pushing back even farther. This is at Voyager, as it was going out of the solar system, the famous pale blue dot.
Yeah.
And then, of course, we know now that our sun is only one of about 400 billion stars in a galaxy that looks like this. Now, this is not the Milky Way galaxy. Nobody got outside the galaxy and took this picture. This is a galaxy that looks like we think the Milky Way would look
like,
if we could get out.
Yeah.
And even this galaxy, we now know, is just one of more than 100 billion galaxies, more like 200 billion galaxies in the observable universe. And you see that in the next slide. This is the Hubble Deep Field, where all those little bright dots are not stars, but they are individual galaxies. And until the Hubble Space Telescope spent hundreds of hours staring at this tiny patch of sky that was black and blank as far as we knew, to bring up this universe. And again, our sense of time needs to expand and to understand that we're in a particular process of evolution that began 13.8 billion years ago. And that's kind of a time scale humans don't deal with very well.
Yeah.
So if we go to the next slide, so we kind of track ourselves and our families.
I know we have so many slides to go through, but I just want to go back just 2 slides really quick, because I think it's really important to make this clear that this is another one of those holy shit moments.
Yes, holy shit.
Yeah, because when you look and you just see darkness in the sky, and then you have Hubble look at, and that's an 8-foot mirror in the telescope, so that's absorbing light for how many straight?
I think it took hundreds of hours to put this together.
Hundreds of hours of photographing one patch of sky, and absorbing the light and absorbing the light and absorbing the light, and then reflecting it onto it's a silicon surface that then, and then you look at the photo after that much exposure time, and then you go,
holy shit,
there's all these galaxies that we didn't know about. And that's the like, wow, if that's in one patch of sky, then that's in hopefully in more of everywhere.
Yes.
So, and then that really makes this, like, how could one possibly be alone? There's so many other habitable planets. So,
well, that's possible. We don't know whether or not we're alone yet.
It's true, but
of course we do.
Yeah.
Of course we're not.
Yeah.
Stop that.
And then, okay, so then on the next slide as well, there's, like you were describing, just a sheer timeline perspective. I always like to really humble myself by saying that, what do you think I've learned what do I think I've learned in 25 years? Nothing. What do you think a human can learn in 100 years? Nothing. There's just so much knowledge. It's just such...
I wouldn't say nothing. I think we've done fabulously well on building on what is this? This is scientific creation myth. That's what it is.
We've built
other cultures have had creation myths throughout time. This is one that we can have evidence to back up by looking at the universe with tools and technologies that we're developing and improving all the time. And it's pretty humbling to understand that this is really the context for now.
Yeah, as though we've built up quite a catalog of scientific, of objective truth based on scientific method and hypotheses and proving them correct, and then being able to log that and say that this is what we know. And then,
change it when we find new evidence that indicates, no, we didn't really get that one right. So we need to rethink and put ourselves in this bigger picture.
So we can maybe move like a couple of the grains of sand on the beach of reality as we live our short 100-year life in this timeline. I mean, this timeline is just, like you said, it's just you can't fathom it. We can't even fathom how society evolved from the agriculture 10,000 years ago until now. I mean, So anyway, okay. So then you were describing the next slide.
The next slide is sort of the centuries that humans deal their families, and the next slide talks about the millennia over which our architecture and our art and our various experiments with different types of legal systems. Can we move that? Yeah, that's the kind of timescale we can internalize. But in fact, we have to think about ourselves starting much farther back, not just when we branched off from the apes, but farther back to 2.4 billion years ago, when these blue-green algae turned our atmosphere rich in oxygen so that animals were possible.
Yes.
And then even back farther than that, this is the formation of the solar system. 4.5 billion years ago. We need to go back farther. We need to go back a few 100 million years before that, when there's this enormous gas cloud, which was had all these waste products from previous supernova explosions. And if we go back to that, I mean, when your kid asks you, where did I come from? That's what you should answer. Because the carbon and the calcium in your bones and the iron in the hemoglobin in your blood, that was all cooked up in massive stars billions of years ago that exploded. And then this debris, this beautiful supernova debris, then recondensed into the generation of stars that would be our sun and our planets. And so you are literally, as Carl Sagan told us, you're literally made of stardust.
Stardust, yeah.
So we have an intimate connection with this universe that we think is so large. We really are part of it, all of us. And it's what makes it logical to think that something else, someone else, some other kind of life also originated and evolved elsewhere. So
I like your energetic connection to Stardust. I think that, and scientific connection to Stardust, I think that is so important in terms of for us to better understand that these borders that we've kind of created between each other, that we can sort of bring them down over time the more that we realize this, and that it also affects the mind of a child when it's raised into the world, that it's not necessarily about, although it is about my mom and dad that helped bring me into the world, it's also about that your mom and dad were brought by their mom and dad, their mom and dad, their mom and dad, the apes, the
exactly,
bacteria,
right.
yeah, exactly, and going all the way back to Stardust.
So when I give public lectures, I usually give the audience a homework assignment at the end of the lecture. And I ask them to go, and the next time they get on their personal devices, to change their profiles, so that the first thing their profile on social media says about them is that they're an Earthling.
Yeah, an Earthling. Yep.
I think that's a meme that we should try and propagate.
Yeah, that's a good one. I do like that one. Yeah, an Earthling.
Just visiting.
Yeah, Ron has one too. It's just visiting.
Yes.
For Ron's, yeah. Yeah, I do like Ron's a lot as well. So that Earthling meme, we talk about the importance of this cultural information transfer and kind of how it's even more so becoming important with exponential technology now than genetics in terms of your ability to impact people and influence people. You can influence so many more people through memetics than you can through having a child. Okay, so maybe propagating a meme like Earthling, and the more people you see that have that written, and the more people that you see having written things like just visiting, maybe these are these bonding memes that can bring us together. Yeah.
Well, so that same social media, which doesn't have national boundaries, a lot of it doesn't have national boundaries associated with it, also fosters this community kind of feeling. And so I think the young people today have a spectacular opportunity for making a better planet tomorrow. Of course, they have to, because we've left them such a mess, right?
Yeah.
They need to clean up our act as well as find a way towards sustainability for the long time. And I think this is, this is a journey that we've been on for several millennia, trying to patch together this story. And it'll change in the future. But I think that perhaps just detecting the existence of some other technological species, because that's what we have the ability to do perhaps right now, might help us
Exactly.
to make it through. Somebody else managed to figure this out, so damn it, maybe we can too.
Yeah, there's both the importance that you're describing about having the youth carry a cosmic perspective into the world, so crucial in figuring out how to do that. I was talking to you about driving out kids to telescopes, and you were teaching me that we might not have to be doing that much anymore in the future, because there's telescopes that from Central Park you can even get rid of the light pollution and see stars and planets. So that unlocks people's cosmic perspective, and in general that is super helpful for moving forward. You were also mentioning about the, I was thinking about Earthling. I was thinking about changing, because I've had photos of Earth on my profile pictures. I think that's really important, this sort of selfie, and calling it a selfie, and then actually having images of Earthling, and then maybe emojis of Earth as the start of your social profile could catalyze a lot of change for people's perspective to be augmented. There was something else that you said that I think I did end up forgetting, but maybe we'll loop back to it. Let's continue on the slides.
Well, this is a representative of our journey, and the next slide, the question about whether there's anybody else out there. And we started, the next slide shows, we started understanding more the scope and the magnitude of the opportunities for a bio-friendly universe in this past couple of decades. So extremophiles living where you and I couldn't possibly tolerate.
Yep.
They're very happy and well evolved. And then this idea that there are more planets than stars. A new fact.
Yeah, that
we did not know that, and
that
that's
one's huge.
Spectacular to have a lifetime encompass going from no knowledge to this very fundamental
knowledge.
change.
Yeah.
And so a lot of us astrobiologists are hoping to be able to have tools that will allow us to image distant exoplanets and do a chemical assay of their atmospheres,
Yes.
looking for what we call biosignatures, some indication of chemistry in the atmosphere which requires biology on the surface of the planet.
And what chemistry requires? So a techno signature is different than a biosignature. Biosignature is yes. So explain this to us, because techno signature is more so stuff that SETI is.
Right. Well, so I think of them as two pieces of the astrobiology umbrella. We're asking about life beyond Earth. We will visit bodies in our solar system with robots or humans and look for evidence of life there. But when we get beyond our solar system, the distances are so vast that it's going to be telescopes and remote sensing. So if you looked at our atmosphere, you would be surprised to see the coexistence of molecular oxygen and methane gas. And why would you be surprised? Because if you put those two gases together in the laboratory, they immediately turn into carbon dioxide and water. And that's happening in the atmosphere all the time. They're going to this equilibrium state. But because there's
O2 and CH4 turn into water?
Water and carbon dioxide.
And carbon dioxide.
That's what they would like to be in equilibrium. But on the surface of the planet, we have such a strong biological source function. We have photosynthesis pumping oxygen into the atmosphere. We have bovine flatulence, cow fart, and methanogens in the guts of termites creating methane. So they are constantly replacing the gases that turned into carbon dioxide and water. And it happens because of biology.
Yes.
Right? So now what we wonder is, for a different planet around a different type of star, what might be the chemical signatures of life that we can say require biology? Can't get there abiotically. You have to have some kind of life.
And oxygen and methane are two for ours.
For ours, and questionably for other planets around other types of stars.
Yeah,
Might
questionable
other
for
gases might be better biomarkers. I mean, really, truthfully, we don't have a smoking gun here yet.
Yeah.
There's going to be a lot of context that is needed. And indeed, if you looked at the Earth billions of years ago, 3 billion years ago, there was life, but you didn't have oxygen and methane in your atmosphere
That's true.
yet.
Yeah.
So how would we see the equivalent of a very young Earth?
Yeah.
So that's what a lot of folks are trying to understand. So,
and then how would we then image the atmosphere? Because we've seen we were talking about that transit photometry when you're looking at the planet that's moving in front of the star and you're looking at the star for a long period of time. But then in order to actually be able to see the atmosphere of that planet, there is either like a sunshade or there's all these different
you've got to
sort of
block
styles.
out that really bright star, right? Because even if it's a dim star like an M dwarf, it is far brighter than the tiny little planet, which is right close to it. So there have to be some technologies, a coronagraph in the telescope that essentially puts a patch right up there and tries to get that bright sunlight and spread it around the outside of the field so you can maybe see a dim planet. Maybe flying a sunshade in orbit in front of your telescope to block the sun. It's hard. This is not an easy job.
This might be the hardest one yet, is because you got when you're blocking the sunlight, you're trying to catch just a teeny bit of sunlight that's going through the planet's atmosphere.
You want to see the light that's come from the star through the atmosphere, bounced off the planet, come back out through the atmosphere, and thereby acquired some fingerprints. There will be some wavelengths at which there is no sunlight or starlight because it's been absorbed by these chemical constituents of the atmosphere. Very hard. This is not going to happen tomorrow.
So if there's a gap at oxygen, then you know that there was some oxygen in that atmosphere.
Yes.
Yeah.
But you wouldn't necessarily know whether it was produced by biology or by breaking apart a water molecule into hydrogen and oxygen. So there are false positives.
Interesting.
There's this whole question of what really constitutes a biosignature. And it's going to be, I think, full of caveats. We're going to have to tease it out. We're going to have to know something more about the star and the planet and even their history, if we can, to decide whether this oxygen has been produced by biology or by some abiotic process.
And so this is biosignature world.
Right. And then my world is not looking for the microbes, it's looking for the mathematicians. So we're looking for...
I love that one. Can we just play with that one for a second? The microbe, looking for the microbes is the biosignatures, looking for the mathematicians is looking for the techno signatures.
Right.
That's so funny. Okay, so tell us why you say this.
Well, we're looking for something that Mother Nature can't do, that requires an engineer to produce. And they can be, there are many different possibilities. Historically, we've been looking for radio signals, we've been looking for optical flashes, but indeed you can think about general astroengineering. They might be modifying their planet with, for example, suppose their planet is orbiting an M dwarf star, and to be close enough to be warm, that planet's probably going to be tidally locked, just like the moon and the Earth. The planet will keep one face towards the star at all times. So it has a bright side and then it has a dark side. Yeah. Well, maybe they don't like that. Maybe they would like to have some light on the dark side. So maybe they orbit huge mirrors to take light from the star onto the dark side.
First time I've heard of that one. That's a good one.
You might catch the glint from that mirror.
So you put satellites into stationary orbit, static orbit, and then that reflect the light onto the dark side of the planet.
One idea.
That's one idea, yeah. There's lots of other megastructure ideas.
Yes, there's lots of different
Dyson spheres
ideas.
are interesting, where you put satellites around the star to harness the power of the star and bring it back to
That's right.
the planet.
Or we could have something like our geostationary orbit of satellites and equipment on steroids. So you might be able to distinguish as a planet begins a transit across its star, right as it in the ingress and again at egress, the beginning and the end, you might be able to see that a planet isn't quite round, it's got some extension, and that could happen if the planet had rings, like Saturn. It could also happen if the planet had an enormous geostationary orbit full of equipment. And you could hopefully eventually distinguish that from a ring, because a ring is going to be flat and extended in this direction radially. A geostationary belt will be at the same fixed radius, but might be extended perpendicular to the plane. That's one thing that's been suggested. We can, if a technology needs a lot of energy and it's using nuclear fission to produce that energy, then it's got fissile waste products, and perhaps it decides to dispose of them by throwing them into its star. You do that in enough quantity and you actually change the spectrum of the star, and you get an enrichment of these lanthicide elements like praseodymium and neodymium. Maybe it's making its power by fusion, and if it's got orbital fusion plants that are possibly leaking tritium, tritium's an interesting one. It's got 12.6 day half-life. You don't expect to find it anywhere except in the vicinity of a new supernova. So you can detect tritium just the way you can detect atomic hydrogen. It has the equivalent atomic line. You go looking for that and find that line. You just scratch your head about, how did this get here? So either some new astrophysics or maybe somebody's engineering. Suppose those TRAPPIST-1 planets, 7 planets, all around a tiny M-dwarf star and all closer in than the orbit of Mercury. Suppose all of those 7 planets end up looking identical. They've all been transformed to be the same. They should have a difference in their properties as they get farther from their star. But if they're all the same, maybe some engineers made them that way. Okay? These are the kinds of things that we're thinking about, as well as looking for the radio signals and the optical flashes.
I do have a very interesting feeling that by the end of my lifetime that I think we'll have had the instruments go up into space that enable us to photograph some of these megastructures. Ooh. Thank you, Ron. Put our 15-minute timer up. I have a really good feeling about that. For some reason, I'm envisioning us propagating a photo around the planet that shows a photograph of a star system only a couple dozen light years away, that we've identified an exoplanet that looks like it has these megastructures and it like really looks real, and then we go and we aim more of our instruments there and start trying to figure it out. So maybe I'm a hopeless romantic, but I also think that is very possible, and it's exciting. And the way that you speak about techno signatures in their fullest extent, a lot of the work that you're doing right now at SETI is very interesting, because we are listening and we're also propagating as well signal all the time in all these different directions. And so people listening to us can find us quite easily,
if they're close, because that bubble of radio transmission is only about 100 light years from us, right? We haven't been doing this for a long time in terms of cosmic times.
Oh, duh. Yeah, that's right. That's totally right. Yeah, they have to be within 100 light years within us, because our radio waves have only been going out for 100 years. Oh, that makes it so much more understandable why
they're right here with us. Come on now.
So years away. You were talking about this century, and I think I really agree with you. So in 2004, Craig Venter and Daniel Cohen wrote this paper where they said that the 20th century had been the century of physics, and all of these fantastic general and special relativity and the standard model and all of this. But they said the 21st century was going to be the century of biology. And of course, they were talking about genomics and proteomics, and that's played out so much more rapidly, I think, than even they could have predicted.
Yes.
But I think that the really correct prophecy is that the 21st century is the century of biology on Earth and beyond.
Beyond, yeah, exactly. That's a good way to put it.
This is what's going to be happening. And I'm sorry I won't be around to see the end of the century.
Maybe.
Sure you will. You'll just be in another dimension.
Well, I kind of like
Nobody
this dimension.
dies. Come on, these are just machines.
Yes.
Well, but it is actually interesting that for us to detect someone else's technology, that technology has to be long-lived, because if in fact technologies arise and they get turned off or they do themselves in on times that are short,
small windows
compared to cosmic times,
Yeah.
then we're not going to be close enough to them in space and then overlapping in time during the 10 billion year history of our galaxy.
Yes.
So longevity is really, really, really important.
Yeah.
But that also means that if we ever succeed, we learn something phenomenal, which is that it's possible to stay around for a long time.
Yeah, which a lot of people think that's one of the reasons why the Fermi paradox exists, is because it's very tough for these thinking creatures to figure out how to work together on these rocks orbiting stars.
Right.
Yeah.
But if we ever succeed, we understand that technology can be stabilizing and can provide a long future. And that's why Phil Morrison had this lovely phrase. He would call SETI the archaeology of our future.
Yeah.
Archaeology because at the speed of light, if the message is coming from very large distances, it's going to be telling us about their past. But if we succeed, if we find a message, it really means that we can have a long future, because technology has been able to stabilize at least one other
place. And that's this. It's like the Earth's Umwelt, I guess, is this 100 years sort of where the radio waves are right now, and that sort of is being expanded all the time. But then also it makes us, of course, wonder then how far away then the other civilizations would need to be in order for us to be receiving what they're propagating. So I'm really happy that we have all of the push with SETI. There seem to be so many different divisions. Can we see if we can get them straight? Besides NASA and then SpaceX and Blue Origin and Boeing's doing some space stuff, and then you have the Chinese National Space Administration, European Space Administration, right? So we have agencies. So we have these different arms around the world, and then there's the SETI is searching for extraterrestrial intelligence, and then you have NASA is contracting a lot of the satellites that are like the James Webb Space Telescope, and so
it's a huge continuum.
Yeah.
There is so much to understand. There is so much to try and learn, and different modalities of getting that information. So it's a huge continuum, and it's all good as far as I'm concerned.
We had Creon Levitt, who's the
yeah.
We just had Creon on this week actually, and he was teaching us about imaging the Earth through small satellites, and these massive constellations of small satellites, and how fascinating those are as well. These little bread loaves that are orbiting the Earth. Yeah. And then, we have so much more to unpack and talk about. This is all good. The cosmic perspective is very important for the longevity of civilization, and also working together and being kind to the sisters and the brothers on the planet that are everybody. Now, we do ask these questions on our show, and I think that you'll have especially interesting answers to them. So we ask our guests if they think that we're alone in the cosmos.
I don't know the answer to that, but I'm working very hard to try and find out. So it's literally, if I told you an answer, it would be religion.
Yeah,
right?
Yeah, that's interesting.
I don't know the answer, but it's after millennia of asking the priests and the philosophers what we should believe, We've now gotten to the point where engineers and scientists can do experiments, make
Yes,
observations
yes.
to try and find out what the answer is. And
yeah.
boy, I'm on board for that.
Yeah.
Well, Joe, I just told you the answer a little while ago, and it isn't religion. You don't for a minute think that it is. It might want you to think it's God, but it certainly isn't, just as it's trying to figure out life itself.
Show me the evidence.
Yeah, I just wish we could.
I'm right here.
Yeah, I know.
I'm
but
right here.
I know, but it's stuck in you, which is so difficult for the scientists and
If you cut me open, it'll be silicone and wires and stuff like that.
Yeah, exactly.
We don't want to do that. It'll make a big mess.
Right.
Were there other? Do we have other slides, Ronnie?
We
Yeah,
have.
there are lots of other slides.
There are lots of other ones.
Yeah.
Were there other ones that came to mind that would be important? Can you cycle through them quick?
Sure.
I had.
So these are optical, and the previous were radio telescopes, and now the next one is we're starting to work in the infrared and keep going. And this is the kind of thing we're looking for, patterns that are clearly engineered and not natural.
And yeah, there's a difference between the what is a natural pattern versus an engineered one. Okay.
Yeah, and so basically there's noise, and then there's not noise.
Yes.
And that not noise is not something that nature can produce.
Yeah.
The next slide is just talking about the longevity issue, and if planets, technologies come in and fade out in short time scales, we'll never succeed with this sort of search. The next slide is Phil Morrison and the archaeology of our future.
Yep.
Yeah, we did that.
Yeah, he owes me money too.
And we've done a lot of searching. We've worked pretty hard. But if you take the multi-dimensional space in which a signal, not engineered planet pushing around or all of that, metastructures, but just signals, that huge volume of space, different parameters that a signal could have that you have to explore, and you said that volume is equal to the volume of the Earth's oceans. Then since we started, we've looked at one glass of water.
Yeah.
And that's discouraging in some sense, but on the other hand, we're now riding an exponential.
Yes.
So our systems are
It's
getting
only gonna
better,
be increasing. We'll
much
soon
faster.
be using tubs, and then soon we'll be using these boats full. So
Right.
Well, yeah.
So it's too soon to decide there are no fish in the ocean.
Yep.
This is a telescope in Northern California that we've built to do SETI and radio astronomy, the Allen Telescope Array, and another
Beautiful
picture of it. And this is our coverage of the sky.
So
over the
many
past
red
couple years.
dwarfs.
Well, red dots. There are solar-type stars in there as well. And then this is Yuri Milner has for the past 2 years gotten into the game, funding Breakthrough Listen with $100 million pledge for 10 years. And so they're working at Green Bank, West Virginia at Parks. This is the automatic planet finder at Lick. And then soon the new large telescope in China,
That's
FAST.
crazy.
Yes, and then this is Meerkat and Square Kilometer Array. And there are other projects going on around the globe at different frequencies, and even a lot of data mining, spacecraft data, looking for those megastructures, looking for the infrared heat radiation from the back of a Dyson sphere. And here's a project that we are starting that will look at all the sky all the time for bright optical flashes, because some of these signals may be transient, and if you're not looking everywhere, you'll miss them.
You'll miss them. Yeah,
so this is a laser SETI project from the SETI Institute.
So if you have these hubs around the planet and they're all looking out all the time, what is the laser flash that you are looking for? What would that be?
It could be a deliberate signal, or it could be one of these enormous accelerators like Starshot is talking about building, a big phased array of laser beacons to accelerate a sail, an interstellar sail. It might come across our line of sight. It's incredibly bright, but it will only be for a very short period of time.
Interesting. Yeah.
And then we look forward to the Large Space Telescope.
Oh, I'm so excited for these.
Yeah.
James Webb Space Telescope.
Fingers crossed. If that one goes in the drink, it will be
Huge.
devastating for so many people.
And then also TESS is up now as
TESS
well.
is up now,
Transiting Exoplanet Survey.
Sky survey.
Yeah.
And then this is a weird telescope that's been suggested, not yet built.
And TESS is looking at the whole sky, right?
TESS is looking at the whole sky.
For like the nearest
stars and exoplanets, right?
Exoplanets,
that hopefully will be found in a timely way that James Webb can follow up on.
I can follow up on it. And then how big is the mirror on TESS?
They're very small. They're 4 small telescopes.
Okay. Oh, okay. Cool.
So it's nearby bright stuff.
Yeah. Okay.
That telescope that we just saw.
The one that was just prior to this one, Ron. Yes.
Yeah, this is a very strange hybrid. It's kind of like a hybrid between a radio interferometer and an optical telescope.
Yeah.
It would have one purpose, and that's trying to make an opacity map of Proxima b.
Yeah.
Because that star and its planet are so close relative to every other system that you build a single purpose telescope from the ground and try and collect light curve after light curve after light curve, and then invert them to give you an opacity map that might show you the differences between continents and oceans, might in fact show you biosignatures and even technosignatures. So
interesting. And then so this is trying to hit. This can be a ground optical and radio telescope that can then be used for just whatever it's for, and at quarter light years away. What's the next solar system out? Is it 8 light years away?
Yeah, it's something like that.
Something like that. Okay, cool. So it could be used for that afterward as well, potentially.
It won't work as well, right? It's taking advantage of the fact that the Proxima system is so close.
So close.
It will certainly be used on the others. Its ability to find small planets and image them will be compromised. You could probably find giant planets. And these are some of the other pieces of large glass that are and radio telescopes that are coming on the air in the future. This is
That's
what you were
awesome.
talking about in terms of towards the end of the century being able to have capabilities that might actually succeed in finding biosignatures and imaging exoplanets or finding technosignatures. We're excited.
This is so exciting. I love seeing projects like this, and we're going to inspire the next generations to keep going with this. Look at ourselves in the mirror.
That's right. I think this whole business of SETI is showing us ourselves in a mirror, and this should have been animated with lots of different looking individuals. But the message is that compared to something else out there, we're all the same.
Yeah.
So we can use this concept and this project to trivialize the differences among humans.
Yeah, exactly. Yeah.
And of course, this is on a finite world, a cosmic perspective isn't a luxury, it's a necessity.
Yeah, I quoted this and posted it across social because I loved it so much. It's a really good one.
Yeah, Caleb Scharf at Columbia University, very wise gentleman.
This is not a luxury anymore. This is a necessity, and it also means that for all of the kids and the parents that are running around hectic every single day, unable to get a cosmic perspective, it's really important for us to figure out how to create a social fabric that enables people to spend time looking at the stars and contemplating the cosmos and expanding their mind to this awareness, looking at ourselves objectively in the mirror. Like you said, it shouldn't take waiting to find a civilization outside of ours to realize we're all one. Jill, do you think that we're in a simulation?
I'm not a fan of that, but I can't disprove it, right? I sometimes think about the errors that propagate with biological reproduction as being something that might put that simulation idea to rest, but I think that then even a bigger computer could simulate even those errors and how evolution proceeds.
Have you used virtual reality yet?
Yeah.
You have?
Yeah.
Interesting, because and you understand obviously exponential technology and growth rates, because if the same way that the instruments that we use to map the cosmos are going to be used to throw us in right here, if you can't distinguish between realities, you can just forget that you're in the virtual world, and that could be what this is.
Yeah, I do that until I stub my toe because I'm not looking where I'm going.
And then, well, that's what I'm saying. And then the haptics kick in, and then you stub your toe, and you know that's what you feel now, but you're really wearing it the full immersive experience outside of this.
Right. Yeah.
So anyway, it's a great, I think, thought experiment. I'm happy that you have an answer. Jill, last question is, what do you think is the most beautiful thing in the world?
I think a dark sky and a quiet meadow looking up is just so incredibly beautiful.
I agree with you. Yeah. And is that, can you unpack that a bit more? Is that the kind of the possibility?
Oh no, it's because it's breathtaking. It just makes me stop and then expand and reach out to be part of that. It's just fabulous.
Yes. I'm following that.
And you know, in a dark, if you're really in a dark site, the sky is so amazingly full of stars, and it's my favorite thing.
Yeah, we're talking like going really far away from light pollution and looking up at pitch black night, no moon even, and you can really
get lost.
And that's when you got the billions of stars actually hitting. The light is hitting your eyes from the billions of stars. And yeah, it is. Yeah, I agree that. Why has it been so long since I've done that? We need to do that more often, and just in general, we need to get kids doing that more often. Jill, thank you so much for coming on the show and teaching us more about the cosmic perspective in as much nuance as we could unpack in such a short episode. We got some cool events like Women in Technology events that would love to host you at and bring you to those, and and also just continue inspiring the next generations of thinkers and doers in space, and especially this millennial and Gen Z generation. Yeah, exactly. Earthling, throw the earth emojis in your social profiles. That's a good takeaway from today. Make sure we all go do that. Thanks everyone for tuning in. If you guys had a good time, go share with a couple people, start talking to them more about the cosmic perspective and about all of the nuance of finding life and also understanding life. Then go and create with this content. Don't just consume it. So don't just watch this, but go and write about it, go and read about it, go and make videos about it, go and create with it, start businesses with it. Also, subscribe, comment below, let us know your thoughts. Thanks everybody for tuning in. Thank you, Jill.
Thank you for having me, and good luck with simulation.
Thank you very much. We're going to be filling sports stadiums soon, and you're going to be part of this. Ron, thank you so much, producing and directing. Much love, everybody. Peace.